I know that perhaps other people don't. So the first thing is that when people say numerical methods, they usually mean what I call a simulation or time-dependent simulation or direct numerical simulation, which is to say it's a perfect experiment, right? You have your equations, your Navier-Stokes equations, are doing, well, we think, we have no evidence that they're not describing fluids. If it's non-Newtonian, you do things. If it's compressible, you do things. But I don't think so far people have found any reason to think Navier-Stokes isn't true. Turbulence, again, as I think I'm emphasized, all turbulent phenomena up to whatever Reynolds number can be simulated are perfectly well reproduced by numerics. That's not, we don't need something more than the Navier-Stokes equations in order to describe turbulence. To understand turbulence is another matter, but to describe it is perfectly adequate. So solving equations, Navier-Stokes, Rees-Ness, whatever, is the same, I'm going to take the point of view anyway, it's the same as doing an experiment, except it's a perfect experiment because you have as much data as you want every place. You have sensors, probes at every place that measure every quantity. It's a perfect experiment, but it can often be a very slow experiment, right? So that's the trade-off. Yeah, okay. So, but that is just, the point of view I'm putting forth to you is that this is only one thing that you can do numerically. People often think it's the only thing, that when they say numerics, they mean this. But you know that we've just done a class in dynamical systems, and we are interested in understanding from a dynamical systems point of view, and what we're interested in is steady states, the fixed points, and their stability. And so the point of view that I'm going to put forth is, let us do more than just a perfect experiment. Let us do things that we cannot do experimentally. Experimentally, we can't go around solving this equation. What the world does is it solves this equation. But we are going to try, we want to understand things by finding fixed points and their stability, and we will try and solve these problems. So that's the main thing I'm going to tell you about, although I will tell you some other things that are not, that are more standard, that are not found in these two messages. Okay? And that's what I mean. So I say that there are 3 tools, probably more than that. You can find limit cycles, you can, but let's see, at least 3 tools. Okay, how many people here have taken a class in numerical methods of some kind? Okay, how many people learned about instability of explicit time time stepping? Explicit versus implicit methods? Okay, good, because that's a good place to start, and that's the kind of the basis that I'm starting from, and then everything will follow from there. Suppose we had the simplest thing, you would never do this numerically, heat equation, periodic boundary conditions, in fact, zeros periodic but only in the half interval, whatever. We have signs, we expand U in signs. Each Fourier mode, each spatial Fourier mode, UK, evolves like dt, du, dt is minus k squared UK. Okay? And of course, you don't need a computer to solve this. The answer is an exponential. So let us write the what happens in a single time step to the exact solution. We take the Fourier coefficient at time t, and it gets multiplied by e to the minus k squared delta t. This is like the initial condition for a time step, and we multiply by the exponential, right, with times time step. And that function here is shown, this is as a function of k squared delta t. This is what the exact solution does. Now let's look at a very simple numerical method, the simplest thing we can do. Let's do a Taylor series. So we have uk of t, and then plus the derivative in time of u, which is minus k squared u times delta t. This is just Taylor series around t. Right? So we gather these terms, and we get 1 minus k, that's multiplying by 1 minus k squared delta t, and that's this green function here. Okay. This green function is 1 at 0, which is the property it shares with this. It better be. If your delta t is 0, you better stay where you are. you're not going anywhere, you're at the same time. And the slope is also -1, which is the slope of that. That's what makes it first order, the first order method, accurate first order. It's got the same, it's got the same value and slope as the exact solution. But the similarity ends there. This is not an exponential, this is a line, and it's going to go to something that's greater than -1 in absolute, it's less than -1, greater than 1. And everybody, if you've taken this class in numerical method, you know that if your time step is too big, if you've exceeded, if k squared delta t is greater than 2, you're going to have a negative value that's greater than -1. This is one of the things we saw in the period doubling class. So each time you're going to be multiplying by something which is negative and greater than 1, and and this is what I've drawn as a function of time. If this is what happens if you are just at k squared delta t is 2, where you're just neutral here. You switch signs, but you don't grow. You shouldn't be switching signs at all. We know that this is all positive. But so you end up growing and explode, and very, very quickly. 5 time steps, 10 time steps. This you know immediately. This is not a problem that lasts very long. And this, I think we discussed this in the class on period doubling. Right? You remember? I think. Hello. Yes. You said, and rightly so. You said, can't we take our continuous time, discrete time to? And I answered at the time. No, generally when we're talking about a real thing, we're talking about a time. But I said for a numerical scheme, that's exactly what happens, and we get period doubling. And that's this what you see here. Is this greater than smaller than -1? This is, okay, I mean, you're not seeing period doubling here, but you're seeing this phenomenon of discrete systems being multiplied by a negative number, and thus leading to alternation. Exactly what you were saying. Okay, so this is forwards Euler. Now, backwards Euler, we do the same thing, except instead of taking the Taylor series at t, we take instead of taking a Taylor series based at t, we take this value at t plus delta t, right? I mean, as I say, I know you know this, but you'll see where I'm going with this. At t plus delta t, we take this over to the other side because these both involve t plus delta t. So we have a 1 plus k squared delta t over on the left. That means that we're multiplying by this rational 1 over 1 plus k squared delta t. And that's what this function looks like. And I think you'll agree that this function looks a whole lot better, more like this one, looks more like the red one than the green one does. These are both first order formulas, meaning that the value here is 1 and the slope is 1, but then the second derivative is wrong. This is true here and here. None of them match the second derivative of this. But qualitatively, this is really quite good and a whole lot better than that. Okay. And of course, we would never do this for the scalar equation. We just know the answer. For a matrix version, supposing we had an operator L, a vector U, and a matrix L, then this matrix version of this is multiplying by this inverse operator, I minus delta T L inverse. And that's what an implicit method is. Okay. So everybody knows that, but I just want, or most people, but I just want to prepare the ground to give you my perspective on it. We'll get back to this very shortly. It's going to be very important. Okay. So we just said these are first order methods. Let's take a little break since I'm going to try and do a little more general things about numerical methods that are not in my main line of thought. So I mentioned these were first order method. What are some second order methods that match the Taylor series also in its second derivative? This Crank-Nicholson. That's, you take the average of the future and the past. Here we took, the forward order was taking the past, the backward order was taking the future. We could average them. Adams-Bashforth, which takes a function not just of the past, but of the past before that. And the third thing, less well known perhaps, is the backwards differentiation formula that takes a formula including the future and the past and the present. How many people know these formulas? Okay, how many people know this formula, Crank-Nicholson? How many people know Adams-Bashforth? How many people know backwards differentiation? Okay. Myself, as a student, and for a long time afterwards, I only knew these. I did not know this one, but it deserves to be better known, and you'll see why in just a moment. These factors that we have been, these functions that we've been looking at, let's look at them for the second order methods. The second order methods, sometimes you need to, okay, it's not quite so simple here. You need to solve a quadratic equation. You might have two amplification factors, but of course what matters, what's going to matter is this one, is the one that's bigger. That is to say, if either of the amplification factors is bigger than 1, then you're in trouble because you'll. And that's what happens with Adams-Bashforth. Here are the two amplification factors, and you can see that you're in trouble if k squared delta t is greater than 1, because again you're negative and multiplying by minus 1. Okay, but I think everybody knows that Adams-Bashforth is an explicit method, and no explicit method can be stable. And we'll say that in just a moment. Why is it an explicit method? Because here you have a formula using the past to get to the future, whereas for Crank-Nicolson or backwards differentiation, you have the future also on the right-hand side. So this is an equation to be solved for un plus 1. We can't replace this by the computer arrow assigned to. This is not a definition of un plus 1 because un plus 1 is here. This is an equation to be satisfied, and so it's more difficult. And same thing with backwards differentiation. But Adams-Bashforth, no, it has all the past, it's only past here, therefore all the ingredients are ready. You could just assign this value to un plus 1. And so that's easier. You don't have to solve an equation, you just have a prescription, you have a formula. But, so why doesn't everybody do that? Because no explicit method can be stable. And we'll say why in just a moment. Anyway, so that's what is being shown here. Adams-Bashforth is an explicit method, and it is unstable, as shown by the Crank-Nicolson. It doesn't explode, that's nice, but it doesn't have very good behavior either. As k squared delta t goes to infinity, you see that you get, that swamps the ones here. You get minus 1, and it's not supposed to go to minus 1. You're supposed to go to 0. Here, people often pay attention to this idea that Crank-Nicolson is a second-order method and hence more accurate, but that only tells you about the behavior here for very small k squared delta t. If you're using an implicit method, that means that you kind of wish to go to big k squared delta t. Otherwise, that's you're taking the trouble to solve an equation. If you're trying to counteract the problem of this, so you want to allow yourself to do k squared delta t, maybe more than 1, for some of the k's. So this isn't very good. Crank-Nicolson may be second order, but it really doesn't have much to recommend. I think that probably you should do backwards Euler rather than Crank-Nicolson. It means that all of those high wave number modes are going to be oscillating. They're not going to be growing, but they're going to be oscillating, and they're not supposed to. They're supposed to be damped. Okay, so now we've looked at these two second order methods. Let's look at this third second order method, backwards differentiation, and look, it goes to 0 as it should, the way the exponential does. And I'm not sure, but I think maybe it's the only one of those three second order methods that goes to 0 as it should for k squared delta t. It goes large. So this is really the best second order method, at least of these three. And not Crank-Nicolson. Crank-Nicolson you should do a backward Euler instead. It really doesn't have anything to recommend it. You have to solve an equation, as shown here, and yet you get this minus 1 thing, which you didn't get for the backward Euler here. You also have to solve an equation, but you get the right behavior. Okay, so that was one little item. We were just talking about stability. I said I would go back to why explicit methods cannot be stable. A stable method has the amplification factor less than 1 in absolute value. What does that mean for q greater than 0? Well, this q is what I was calling k squared here. That's to say, of course, things don't always have to decay. Supposing your equation grows. Well, if your equation grows, you'd like your solution to grow too. But the way we're measuring things is on decaying solutions. That's what stability analysis consists of. It's the one thing that we can do. If your mode is decaying, are you capturing that with your numerical scheme? And so that what's called q there is this minus k squared. Yes, I think so, right? No, it's k squared. It's k squared. Okay, so your real solution is to be sorry, it's supposed to be e to the minus q. Explicit methods all are an approximation of the exponential is the exact one. People tend to forget that, but that's really your goal, is to approximate an exponential. Explicit methods, necessarily, they're approximating the exponential by a polynomial. And we know that polynomials are unbounded. All polynomials, they may do, all kinds of interesting, who knows what. But eventually, they're going to go to infinity, right, on both ends. So this tells you an explicit method, if you accept the fact that an explicit method is the representation of the exponential by a polynomial, no explicit method can ever be stable. Implicit methods approximate the exponential by a rational. And that's why we saw that here, the simplest one, 1 over 1 plus k squared delta t. So this is what we've already said. To be stable, the method must be implicit. In addition, and this is something I'm not showing, and I don't know how to show it. I mean, it's shown probably in most classic texts, but I don't know the proof. You cannot make a method of higher than second order that is stable. You've seen that backwards differentiation is stable, Crank-Nicolson is stable, and backwards Euler are stable. None of them blow up as you go down this axis. But apparently, you cannot have a third order method that matches all those derivatives, the value, the slope, the second derivative, and the third derivative, and also be stable. Again, I don't have anything except just to state that. An implicit method, as we said, you have to solve for u of t plus delta t. Even if you have a linear equation, that can be difficult. That means you have to solve a linear system. If your u is a velocity field in 3 dimensions, x, y, z, and you've done a resolution of 100 by 100 by 100, which is not all that much, right? Then you're talking about a vector of length 10 to the 6th, and you're talking about matrices that are 10 to the 6th by 10 to the 6th. And say this is time dependent, by which I mean, obviously, computers progress, and what was possible, what was impossible when I was a student is more than possible now. I have much more power here than I had in the computer that I used, that I had went over phone wires to use, a big national supercomputer. Everybody knows that. Still, there's always a limit. And not only is there always a limit, these things are growing by, you can see in several ways. If you increase each dimension by 10, that's increasing the total number of unknowns by 1,000. In addition, the obvious matrix algorithms, both Gaussian elimination for solving systems or QR for finding eigenvalues, they scale like the cube of the number of unknowns. The cube. So if your problem size is 10 times bigger, then that means you're taking 1,000 times as long. But we've already seen, if you just want to make one spatial dimension 10 times bigger, the number of unknowns is 1,000 times bigger. And so you have 10 to the 3 to the 3, 10 to the 9th. And that's just from increasing the number of spatial points by 10 in one direction. That is not even am I right? Do I have this right? 10 to the 6th is 1,000,000. Am I right?
Yeah.
Right? So 10 to the 9, 10 to the 6th. Oh, and to the 3. Oh, that's 10 to the 18th. No, I don't think we have a word for that. Do we? 10 to the 18th? Well, maybe. Anyway, I think I've done that right. That if we want to take each direction and increase the number of spatial points by 10, that's going to increase the number of unknowns by 1,000. And since algorithms scale like 10 to the 3 themselves, then that's 10 to the 3 to the 3. I'm doing this right, am I not? Why is this that big? 10 to the 3 to the 3. What's 10 to the 3 to the 3? No. I'm doing, okay, hold on. 10 to the 6th, no. Yeah, 10 to the 3 to the 3 is 10 to the 9th. Right, so not 10 to the 18th. Am I right? Yeah, okay. We have a word for that, surely. 10 to the 9th is a trillion. No? I can't believe you're filming me. Asking these silly questions. Anyway, you can see it's easy to be limited. Even if computers are getting bigger, and of course they're getting bigger at a very fast rate, but those are pretty big numbers. Whether they're 10 to the 9th or 10 to the 18th, they're pretty big numbers. And in fact, solving large systems, linear systems even, is the main difficulty in computational fluid dynamics. It always has been, and I think probably always will be. And one of the reasons we have to solve systems is what we said, we're doing an implicit method. So an implicit method consists of an equation that you must solve for un plus 1. And that's true even if you're merely doing a linear equation, you must solve this system. Okay, we'll get back to this point shortly.
Excuse me?
Yes.
The comment you made about being at most second order.
Yes.
So when we increase the order, is that it will become unstable or it will become computationally very expensive?
No, it will become unstable. At least that's the statement I'm making. I have no idea where I saw that or what the proof is, but I must have believed it at some point. I must have seen it at some point. But yes, it will become unstable. Any formula that's third order accurate will be unstable.
You are meaning unconditionally unstable.
I'm sorry?
Unconditionally stable.
Whatever it is that I meant here, this thing here. I know there's different definitions. I learned to call this A-stable.
I mean, is when you mean by, for let's say higher order time integration method, like
Yes.
third order, fourth order, you mean there are no so-called unconditionally stable. So that means for all range of delta t that you consider,
Yes.
there's no such kind of schemes that can be unconditionally stable for delta t.
Well, I just say I mean what I've written here. Other words. I don't know the other words. I'm talking about trying to integrate du dt equals minus qu. And the question is, will this decay for all delta t?
Okay, yeah. For all delta t, yeah.
And I claim, apparently at some point, that you cannot do that in a third order accurate way. Okay, so we're going to talk just a little bit more. Let's see, we'll get back to my main point about here. Let's go back a little bit here. So let's talk about matrix solution. Supposing we'll see why we have this form here. Supposing we wanted to solve for u, S is a right-hand side. And again, this is big, maybe it's a velocity field, not just 1 million, but 10 million, 3 million unknowns. If the matrix is of a particular kind, then multiplication, normally multiplication takes a time n squared in the number of, where n is the number of unknowns. And here the number of unknowns is 1 million. I'm just talking about matrix multiplication. Usually people talk about sparse versus full matrices, and if your matrix has mostly zeros, and if you know where those zeros are, which you usually do, then of course it's not going to take a time that's m squared. It's got to take, matrix multiplication must take in general a time m squared, because it's going to take their m squared elements, and for you to touch every element would take a time m squared. Obviously it can't be independent of an element, and they're m squared elements, so of course it takes a time m squared. We know of some operations that do not take sparse matrices. That's not the case because they're zeros, if you know that they're zeros. But there's another important operation, matrix vector multiplication, that does not take a time n squared, despite not being sparse, and that's Fourier transform. Fourier transform, we know it takes a time n log n, right? Not time n squared. And yet, the Fourier transform is full. Each of these elements is something like e to the I j k pi over n or something, right? Each of these, the jkth element is something like this. I'm not sure I have that right. There's pi maybe is someplace else, but okay. But anyway, it's full, and yet it takes a time that's less than n squared. And that is because of the nature of the matrix. But in fact, it's better than that, much better than that. People usually think about that fast Fourier transform, but there's an aspect that makes it even more economical if you are taking a 2D or 3D Fourier transform. If you take, you have one in X, and one in Y, and one in Z. Taking a 3D Fourier transform means multiplying by an NZ by NZ matrix. Forget about the fast aspect for the moment. So that takes a time NZ squared. And these just stay the same. That's the third dimension. In the second dimension, you're multiplying by an NY by NY matrix. And that takes a time NY squared. I should have said NZ squared, yes, but there are NX and Y of them. You're taking NX and Y Z transforms. You're also taking, now you're going to do the transform in the Y direction. You take NX NZ Y transforms. And then you're taking your X transform, so that takes a time NX squared. It doesn't even, not even taking into account the log. That's NX squared, but there are NY and Z of them. And you add all that up, and that's NX, NY, NZ times NX plus NY plus NZ. Which is a whole lot less than the square, which would have been NX, NY, NZ squared times NX plus times NY times NZ. And of course, there's the fast aspect of it, which is that the actual fast Fourier transform in 3D is going to take a time that's NX, NY, NZ log NX, because you have NX log NX, log NY, log NZ, and that becomes NX, NY, NZ log of NX, NY, NZ. So this tells us that when matrices are structured, look at the words that I used. The words I said we're going to take an X Fourier transform, but there are NY and Z of them. We're going to take a Y Fourier transform, but there are NX and Z of them. That implies a matrix structure that's kind of like that's block diagonal effectively. If you were in 2D, you'd have an NX by NX block. This would be NY. This would be the first. And so on. So these are actually there's the Fourier transform aspect, but there's also this sparse aspect that they're diagonal in those other directions. So indeed, when we do any kind of, I was a little bit misleading over here, because when I said here that I said we had 100 by 100 by 100 grid, and I said that that means that we have vectors of length 10 to the 6th, 1,000,000, that part's true. But the idea that then matrix operations take a time that's cubic in that's not really true, because whenever we get matrices that are that big, no, I shouldn't say that. Whenever we get matrices that are that big, there are other people, maybe in, I don't know, in communications or data science, other fields I don't know about, things like Google counting all the people who access this and that. I don't know anything about their matrices. But I know about our matrices, and the fact that they are large comes from the spatial discretization. So those entries are not all related to everything. We know that they have structures like this. They're not just some matrix that needs to be treated with a matrix solver. Yet, some people think that, even in CFD, and I see people actually making matrices and giving them to general matrix multipliers, general matrix solvers, which is very, very uneconomical,